Great. So yeah, in until now, so we saw the non-linear dependency of R on or R switch basically on V in or basically the input signal. So our R switch was basically R on itself with a linear dependency, but along with it, we also had some non-linear dependencies, which was R1 V in and R2 V in square. So what we approximated was the drop across the capacitor as the input voltage itself in order to approximate the drop across the switch R switch itself. So uh, for a sinusoidal input voltage, let's take it a sinusoidal. So then in previous video, we had a huge equation for the voltage across the switch, right? So using intuitions, we can neglect or ignore few parts of that huge equation, and we can drop down to these three values of or these three parts of equation. So it's the voltage drop has three contribution basically. So this is the linear dependency, and this one is basically the second harmonic, which is this dependency, and this one is the third harmonic. So basically the voltage drop across the switch is given by this equation. So, and we have the plus signs in between. So this is a complete whole equation. So then the drop across the switch is given by this equation, and all the drops are proportional to these terms, C omega n, C omega n. So basically all the drops are proportional to C times omega n, because the drop is nothing but voltage across the switch, right? So it's nothing but voltage equals to current times resistance. And if the current increases through the capacitor, when the frequency increases, also if the value of capacitor increases, then the current itself increases, because we know current equals to C dV by dt. So if the value of C increases, then current will increase. Along with that, if the frequency increases, so then also the current will increase. So basically the current or the drop is proportional to C times omega n. So basically on the value of capacitor and on the value of frequency. So as far as the track and hold is concerned, we can model the voltage drop across the switch, which is Vx, as the voltage drop separately. So what we are doing basically is what we do is we whatever the voltage drop we are getting, so we will put it in a box and we'll say that this is the amount of voltage drop we're getting across the switch, and then we will take the ideal switch. So we can put it or separate it out in this manner. So what benefit will it provide to us? So this voltage drop is basically in series with the input voltage. So our V in will be VCM plus A sine omega t, as we have considered the sinusoidal input, which is over here. And in series, we also have one more voltage, which is the voltage drop across the switch. And then we have our ideal switch. So then it appears as if an ideal sample and hold having input, which is, so now the switch has the input this voltage plus this voltage. So basically, but then again, V in is analog, so it is going up and down. So it has its positive and as well as negative cycles. So basically, Vn plus minus Vx is the input to our ideal switch, and we know how our ideal switch works. All we are trying to eliminate the non-idealities, and like if we have had a ideal switch, then it was not a problem and not a big deal at all. But now we can take an ideal switch by realizing the voltage across it, which is due to non-ideality. We can club it up with the input voltage itself. So what happens then? So basically the question is, what would be the ratio of the second harmonic to the fundamental of the actual input voltage at this point, at this particular point? So we have our second harmonic we had our third harmonic, and we had our original whatever input is. So at this point we have to measure. So it is basically a measure of whatever the distortion we are getting due to non-ideality, or how much the non-linearity there is in the track and hold. And this is called basically a second harmonic distortion. So this ratio basically is given by harmonic distortion. So it's basically this value, second harmonic, divided by the original tone. So this divided by this. So this gives us HD2, which comes up to this value. So it is basically Ca omega n times R1 by 2. And similarly, the HD3 is basically again third harmonic divided by the first harmonic, third harmonic divided by the original one, which is Ca square omega n times R2 divided by 4. So this merely comes from these equations. So like what we have as of now, so we have our switch, and that switch has its own non-idealities, has its own distortion. And let's say we are sampling the input signal at frequency f of s, which means the input is lesser than f of s by 2. We know this, right, from our previous videos. So the bandwidth will be till f of s by 2. So basically the input will lie lesser than fs by 2 if the sampling frequency is fs. So given that, uh, we can we have anti-aliasing filter, and we are using that filter, and also we are taking care of the fact that there is no aliasing. So if the input lies between 0 to fs by 2, where will the second harmonic will lie? So it can occur potentially from 0 to fs, and the sampling is happening after the anti-aliasing filter itself. So the second harmonic might not get filtered out, because the second harmonic also lies between 0 to fs, right? And as we know that the anti-aliasing filter has a bandwidth of fs by 2, or like 2b maybe. So there might be a possibility where the second harmonic might not get filtered out, and thus even though the input is input to the sampler is band limited by using anti-aliasing filter, still the second harmonic can appear at the sampler. And when we sample this, the second harmonic can appear in the discrete domain as a low frequency discrete tone in the output. So that's basically the noise or the distortion. So let's say, to elaborate this using an example, we have input frequency at 400 kilohertz. So then again, using Nyquist theorem, let's say we have our sampling frequency more than twice the input frequency, which is more than 800. So let's take it 1 megahertz. So now second harmonic will come at 800 kilohertz. So why? So 2 times Fin is basically 800 kilohertz. And if switch is non-linear, we saw the non-linearity of switch. So if the switch is non-linear, it's like adding a component of like adding a component at 800 kilohertz, and also at 1.2 megahertz, like twice the Fin and thrice the Fin. So before the ideal sampler, which we have over here, so it's like when we realize the what we say, the drop across the switch, which is Vx, when we realize this in this manner, so it's just like adding a component of 800 kilohertz and 1.2 megahertz before the ideal sampler. So if we sample 800, like now we have that harmonic in the input, right? So if we sample 800 kilohertz at sampling rate of 1 kilohertz, our sampling rate is basically 1 megahertz, so 1000 kilohertz, basically that's the same thing. So if we sample 800 kilohertz at the sampling rate of 1 megahertz, it will give a tone in discrete time. So that tone will look like as if it is coming from a continuous time input signal which was at 200 kilohertz. So even though there is no signal such like that, but due to this harmonic, when we sample that second harmonic at this sampling frequency, then in the output we will get that tone. We will get that tone in discrete time, and that tone will look like as if it comes from a continuous time signal, which signal was at 200 kilohertz. So that's the logic behind it. Similarly, when we talk about 3 times fin, so basically when we talk about 1.2 megahertz, so again, when it is sampled at our sampling frequency, which is 1 megahertz, it will give us a tone in a discrete domain or output, which will look as if it comes from the continuous time input of 200 kilohertz. So if we have a continuous time signal and we pass through a non-linear sampler or non-linear sampling switch, so the harmonics will appear at each the harmonics will definitely appear even though we have band limited and anti-aliasing filter, and each harmonic will be higher than the fundamental. So this so basically we have this one as our fundamental, this is our second harmonic, this is our third harmonic. So we saw that harmonic will come and that will be greater than the fundamental itself. So that's how we say that when we pass the input or the continuous time signal through a nonlinear sampler, it basically means that the harmonics will appear and each harmonic will be higher than the fundamental itself when seen in the continuous spectrum. And these harmonics can lie at frequencies which are less than the input frequencies because of aliasing. So now we discussed that these are the non-idealities, or this is how the distortion lies in our sampling switch or the sample and hold. So now let's say we have this switch, non-ideal switch, and we applied input to that switch and we got the distortion. So now the question is, how much distortion can we tolerate? So we know for sure that there will be, first thing, there will be a thermal noise. For that thermal noise, we said that okay, we can bear such kind of thermal noise so that we will get maximum bandwidth for our track phase. So using the value of kt by c, we said that we will use c sufficiently high in order to reduce the thermal noise significantly. But now we, along with thermal noise, we also will be having distortion, and that distortion will come due to the non-linearity of that switch itself. So the question is that how much distortion can we basically tolerate, or in other words, how can we comment that the sampler we made is good enough, as for is good enough or not as far as the non-linearity of the switch is concerned. So basically the ratio we talked about, which was hd2 and hd3, so it must have upper limit. What do I mean by that? So one way of we need a thresholding for the upper limit. One way of thresholding what hd2 and hd3 are acceptable is to say that the error due to the distortion must be less than some fraction of the quantization. So quantization is, we have a, like when we have our discrete samples ready, so we pass them through a quantizer for amplitude quantization. So I have shared you the figure when we go from the sampled discrete time signal to a discrete amplitude signal. So when we try to make levels while quantization, so we make sure that the error due to the distortion while sampling must be less than some fraction of that level of quantization. So we have our values of these ratios, or ratios for SD2 and SD3 corresponding to the first and second and the third harmonic. So hence the input amplitude and the input frequency are fixed. So input amplitude and input frequency are fixed by the signal itself, so we can play over there. Let's also say that the capacitor is also set in such a way that the signal to thermal noise ratio, we are not talking about thermal noise, we have covered thermal noise already. So here we are talking about distortion due to the non-ideality of the switch. So let's say the capacitor is also set in such a way that the signal to the thermal noise ratio is adequate, and it is given by a square c by 2 kt, which is the signal to noise ratio when we talk about the thermal noise, not distortion. So over here, one can say that if we put two larger amplitude as input, so if the input has too large amplitude, then what will happen? The SD2 goes like increases, and the SD3 goes up by a square. So this is the amplitude, right? So if the amplitude is too large, so then SD2 will be too large, and SD3 will be even more larger. It is proportional to square of that value. And due to the proportion, like this is due to the proportionality of these non-linear components towards the amplitude square and amplitude cube. So we can obviously reduce the amplitude of the input. So to resolve this situation, we can think that yeah, obviously we can reduce the amplitude of the input, right? So anyway, it's directly proportional to the HD2 and HD3. So but what happens, so if we reduce the amplitude by a factor of 2, so what happens over here is, if we reduce the amplitude by a factor of 2, then HD2 will reduce by a factor of 2, and HD3 will reduce by a factor of 4. So then what happens to the signal to the thermal noise ratio? So what happens to the SNR when we talk about the thermal noise? So again, if we decrease or reduce the amplitude by the factor of 2, then this is directly proportional to the squared of amplitude. So it will go down by the factor of 4. But we want our signal to noise ratio not go down, because the capacitor is adequately fixed and we don't want that SNR to go down. So what we do then, we have to anyway increase the capacitance by the factor of 4, because it's going down by factor of 4. And to maintain this SNR, we have to increase the capacitor by a factor of 4. So then uh, when capacitance is increased by the factor of 4, the current through capacitor will increase by the factor of 2, because you can refer to the equation of the current through that capacitor. And when you look at that equation of the current, we'll see that if the capacitor increases by the factor of 4, then the current through the capacitor increases by the factor of 2, which means that the distortion components HD2 and HD3 are basically what we are doing is, we are reducing amplitude by 2, in order that we will say that anyway it's proportional to the HD, right? And we want to put a upper limit to this, so we want these as minimal as possible in order to gain higher resolution, right? So but to get this lower, like to get the values or the contribution of these SD2 and SD3 to lower down, C is fixed, omega n is fixed. So we tried to make the amplitude of the input lesser. So we took it a by 2. So then when we are taking it a by 2, we saw here, we discussed what happens to other factors. So if we take this down by a factor of 2, then we have to increase the capacitor by factor of 4. Same goes with HD3. So what happens is, so initially, if we see at this again, so SD2 has increased by the factor of 2. Instead of reducing, it increases by the factor of 2. And SD3, instead of reducing, it remains as it is. So you can equate these numbers and play around, and you can figure it out that in order to decrease the distortion components due to the nonlinear effect of switch, if we decrease the input amplitude, it turns out against us. So then obviously that's not the right way to do it or solve the problem. So the obvious choice we are left with is C gone, A gone, omega in is already fixed. So we are left with is R1 and R2. And R1 and R2 are the resistances which are dependent on the input voltage. So they are the function of input voltage, and input voltage is basically varying. So then R1 and R2 are non-linear components, and that's where the complexity lies in, right? That's what we are trying to resolve. So then we need to reduce the effect of the non-linearity caused by R1 and R2, which means we need to make the resistance of the switch as independent as possible of the input signal. So we need to make R1 and R2. They are basically dependent on input signal, right? Input voltage, or let's say input signal, both are the same thing. So we need to make the resistance of the switch as independent of signal as possible. So then again, visiting the switch we used. So basically this is our source, right? And our VGS. So this is our input, which is VCM plus Vin. So our VGS is basically voltage at gate minus voltage at source, which is we said that in a track phase we will provide VDD. So it's VGS in track phase is VDD minus VCM minus Vin. We saw this equation earlier, and the resistance of switch is inversely proportional to VGS minus VT. So we saw these equations in last video as well. But the VGS, so the source is varying, right? So the input voltage is varying. So source is varying. So if source is varying, VGS is varying, and that's what this non-linearity occurs. So as of now, let's ignore this VT, and let's say the variation of VT due to the body effect is neglectable, and let's assume it as a constant. So let's focus on VGS. So what do you guys think, that this VGS is causing a problem, right? Because our like the resistance of the switch is inversely proportional to VGS, and VGS is varying, so the resistance will vary and non-idealities will occur. So then let's say that when the input varies, VGS varies, which in turn results in varying RSW, or the switch resistance. Let's say the solution is basically if VGS was independent of the input. So what if the VGS was independent of the input itself? Then our switch will be independent of input, resulting in a linear operation, and then the problem will be solved, right? So what we are basically saying is that instead of VDD, because this was fixed, right, and the source was varying. So what if somehow we make VGS independent of input voltage? So then basically we mean is we have our input voltage. So what we give at gate is basically VBAT plus Vin plus VCM. So this and the input cancel out their effect, and it makes the gate voltage or the source voltage be independent of the input voltage. So this is when we have a tracking phase, and in hold phase we want our switch to be open. So we don't want this MOSFET to be working condition, so we just provide 0 or the ground to the gate. So this is in hold phase, but in track phase where we are most interested at, so that's how we can make the VGS independent of the input voltage. So the most straightforward way of implementing this, so earlier we said that at this point, or at gate, we simply gave VDD, but we saw the effect of VGS. So easiest or straightforward way to apply this VBAT. So VBAT is basically voltage of a battery. Let's say voltage coming from a battery. So applying VBAT plus Vin plus VCM at gate is basically we have our input, right? So this input goes to source, but it also goes to VBAT. So VBAT adds up with the input, and it goes to the gate. So then at gate we will be having VBAT plus VIN plus VCM, and the VBAT is the only needed in track phase of the clock cycle. So we need this only in track phase, not in the whole phase. And one more thing, current does not pass through gate. Gate provides infinite resistance. In latest CMOS technologies, there is amount of current leakage in the gate as well. But as of now, that's not of our concern. Let's say there is no current through VBAT basically. So that's how we implement it. So I need you guys to think that how can we implement such kind of a system. So what are different ways to implement um, such kind of a system? And I want you guys to come up with ideas in next video. So that's all for this video, and I think I have laid a nice idea to resolve the issue of distortion. So yeah, like that's all for this video. Thank you so much. So if you guys have any doubts, please do ask me.